second session today, and our first speaker is Arthur Parzygnat, who will talk on categorical probability in the quantum realm. Arthur, over to you.
Thank you. Thank you very much. I'd also like to thank Rory for initially inviting me. And I have to apologize for not being able to make it in person. But it ended up, the fact that we have this pandemic, I was actually able to make it virtually. So thanks, Tobias, for re-inviting me. And also thanks, Paolo, for helping a lot with the technical aspects of this conference. So today I'm going to talk about Markov categories, but in the context of quantum mechanics, and the fact that you can actually also do a lot of probability theory in that context, and you don't necessarily need a commutative structure to be able to do that. So that'll mainly be what I'll talk about today. And feel free to stop me at any point if you have any questions or anything like that. I'm more than happy to. I would prefer that you get something out of this talk rather than for me to finish everything that I have prepared. So definitely feel free to do that. This was working a second ago, no? Okay, if that gets annoying, then I'll just switch. So the main topics that I'll hit, I'll introduce the category of finite dimensional C-star algebras, and then I'll talk about the quantum Markov categories that you can associate with that category, specific subcategories of that one, which will be convenient for making a probabilistic, having probabilistic interpretations, and the different notions of positivity that could occur in these different subcategories. And if I have enough time, I'll talk about applications, in particular no cloning theorem and quantum mechanics, disintegrations, and Bayesian inversion. And 90% of this talk roughly is based on a recent preprint of mine, and then another 10% is roughly based on joint work with Benjamin Russo, who's at SUNY Farmingdale in New York. Oof. Yeah, this might be a little too annoying, huh? Sorry, do you think you actually might be able to swat me? That's not sliding as much as I'd like it to. Paolo?
Sure, no problem. So unshare your screen there. Unshare your screen there.
Yeah, exactly.
And share your screen here.
Okay, perfect. Okay, this will probably be easier. Okay, great. So the category that I'm going to introduce is finite dimensional C-star algebras. And if you don't know anything about C-star algebras, that's completely fine, because you can just think of matrix algebras. So these are going to be, you can think of them as vectors of matrices, where the multiplication is given by pointwise multiplication. And once you're in a certain component, you just multiply those matrices together. And there's going to be, you can also take the conjugate transpose of matrices, and you could do that component-wise. There's a unit by putting the unit at every single entry, by taking the identity matrix. And you can also compute the operator norm of each of these matrices. And all of this structured together just tells you that you have a C-star algebra. But if you're not comfortable with that language, you can feel free to think of these examples as the main objects of the category that we'll be working with. And the main thing that we'll distinguish between different categories are actually going to be their morphisms. So the most general class of morphisms that we'll be using are going to be linear unital maps or conjugate linear unital maps. So the latter just means that if you plug in a complex number and you apply your function to that specific matrix, then that number gets pulled out complex conjugated. And you might ask if there's a tensor product structure on this category, because if we're going to be reasoning string-diagrammatically, we're definitely going to need a monoidal structure. And although you can take the tensor product of linear maps to get a linear map, and you can take the tensor product of conjugate linear maps to get a conjugate linear map, you can't take the tensor product of a linear one with a conjugate linear one. And you can quickly check this by like a rough calculation. If you take f as being linear and g as being conjugate linear, then on the one hand, you can compute the tensor product of the two maps. You can try to define it this way. And on the one hand, if you pull through the complex number after you apply these two maps, if you pull through on the left, you'll get a complex conjugate. But if you pull through on the right map, you'll just get that same number back. And these two aren't equal, so it doesn't even make sense to take the tensor product of two different such morphisms. Nevertheless, you can make sense of a tensor product structure. It's just going to be partially defined. So what this means is that that's exactly what I said earlier. You can take the tensor product of linear ones and tensor product of conjugate linear ones, but you can't mix. And you might wonder if there's actually a mathematical structure behind this. And there is. It's called a G-graded monodal category that was introduced by Froelich and Wall quite a while ago, actually. And in our case, we're only going to be working with G-graded monodal categories where G is either trivial or Z mod 2. And there's also going to be a unit, there's going to be a unit in this category as well for the partially defined monodal structure that satisfies the usual axioms of what a monodal unit should satisfy.
Is that the same thing as a involutive category as defined by Bart Jacobs?
I don't know the definition offhand right now of that.
Yeah, fair enough. I can ask you later.
Excellent, thank you. So we're gonna introduce what I'm gonna call a quantum Markov category. And it's going to be very similar to an ordinary Markov category with just a few minor differences. So we're gonna assume that it's a Z2 graded monodal category, and it's equipped together, and each object is equipped with a set of morphisms. First, you'll have a copy map, which takes it's essentially a product map. And we're gonna have a discard map, which is a map from the unit to A, and an involution on A from A to itself. And you can depict them all string diagrammatically as you normally would for copy, discard, and then we just introduce another notation for this self map. And these morphisms are required to satisfy several conditions. And the conditions that are here most of them should look very familiar. These are the usual assumptions that are the usual conditions for an ordinary Markov category. But I think it helps a lot to go through each of what these looks like in the examples that I'll have in mind, which is the category of finite dimensional C-star algebras. So the first axiom that I wrote here is just telling you that multiplication is unital with respect to the unit in your algebra. The second axiom is just associativity of the multiplication. And by the way, if you're maybe confused about the difference in notation, because I'm working with algebras, I'm going to be reading the maps from top to bottom, and as opposed to from bottom to top, where I'm thinking of sets. And the reason is because you should think of algebras and the morphisms between them as sort of like the opposite category of sets and spaces and morphisms between them. So going back to these different string diagrams, the third one is probably the one that I would say looks the most strange. But when you think about it in terms of star algebra, all it's saying is that when you take the product of two matrices and compute the conjugate transpose, it's the same thing as computing the conjugate transpose and multiplying them in the opposite order. So that's why this string diagram encodes that information. And then the other diagrams are fairly similar. Grounding the tensor product is the same thing as taking the tensor product of each of the grounding, which is just a statement about the units. Grounding acts as the identity for the unit in your category. The tensor product satisfies the interchange law with respect to the multiplication map or the copy map. The involution is indeed an involution, so it squares the identity. The involution on the tensor product distributes over. The involution is natural with respect to grounding, and a lot of these other axioms. So the identity, multiplication on the identity essentially does nothing. It's just multiplication. And we're also going to assume for today that when you ground any even morphism, you just get back the grounding. And when you ground any odd morphism, you get back almost the grounding, but possibly with a complex conjugation. And this is just going to encompass the fact that we're working with probability preserving morphisms in the categories that we'll be working with. So again, these are what those string diagrams look like without the equations that we had. So I want to distinguish these quantum Markov categories and the classical ones that appear in the literature and Cho, Jacobs, and also Fritz's work, for instance. And what we can do is we can look at a subcategory of our Markov category. And if it satisfies this additional axiom, which says that the involution is natural with respect to the duplication map, then that subcategory is said to be a classical Markov subcategory. And you can rederive the usual axioms of a classical Markov category from this by just checking to make sure that the duplication is indeed symmetric. And this isn't really, it's fun working with these diagrams to check that you can, that you feel comfortable with how these computations work. For instance, you can use the fact that the involution is squares to the identity. You can try to pull that through the copy map using the above assumption. And then you can use the axiom that I showed earlier on how the involution passes through the multiplication map, and then using the involution squared equals the identity, again, we get back the copy map. So this actually reproduces the usual definition of a Markov category. And just a comment that if you work with the subcategory of commutative finite dimensional C-star algebras and positive unital maps, which I'll review in a moment, then that's going to be equivalent to the category of, the opposite of the category of finite sets and stochastic matrices between them. In that case, you're just reading the map, you're just reading the diagram from bottom up instead of from top to bottom. So I want to distinguish several different notions, several different classes of morphisms inside this category. And this distinction does not exist for the commutative setting. So we're going to start off with the simplest assumption we can make. And for that, I need to review positivity. And it's something that you'll feel comfortable with once, I hope, once I mention this. So if you take an element of a C-star algebra, then it's said to be positive if it's the square of something. And when I say the square of something, I really mean that you take the adjoint of that thing with itself and multiply the two together. And a linear map from one C-star algebra to another is positive if it preserves that structure. So I really want to give an example for you to think about when you think about this thing, if it's new to you, is that if you take just an ordinary matrix algebra, so m by n matrices, then such a matrix is positive if and only if it's both self-adjoint and its eigenvalues are non-negative. So actually when I say positive, I don't mean strictly positive in the usual, in the linear algebraic sense. I mean positive semi-definite. And an example of a positive unital map is a map that just takes the transpose of a matrix, right? So if you take the transpose of a matrix and you start off with something that's self-adjoint, it's still self-adjoint. And if it had non-negative eigenvalues, then the transpose also has non-negative eigenvalues. So it is indeed positive. So this, it turns out that you can compose positive maps, and that forms a subcategory of the initial category that we had introduced earlier. So if the notation gets a little bit bothersome, I think it's helpful just to look at the last 2 or 3 letters. Positive, P stands for positive, U is for unital, and we'll introduce some more notions of positivity in a moment. So Another notion of positivity, slightly stronger than the previous one that I just introduced, is that of Schwarz positivity. So Schwarz positivity is it's a linear, first of all, it's a linear map, and it satisfies a certain inequality, which says if you apply the square of if you apply a map to a square of an element, then that's going to be bigger than or equal to applying that map to each of those elements and then squaring them. And since we're going to be working with unital maps, that coefficient in front won't be there. So it's a fact that every Schwarz positive map is positive, and you can see this by just dividing that norm on both sides when it's non-zero. But the converse is not true. And here's the example that we actually gave before is such an example. So the transpose map that takes a matrix to its transpose is positive unital, but it does not satisfy this inequality. And it's kind of fun just checking that we make sure that we understand this. If you just take the matrix B, which is 0, 0, 1, 0 on the right-hand side here, can you see when I highlight? Oh, great. So you can take this matrix as B, take its conjugate transpose, get the one on the left, multiply the two. Well, what do you get? If you do matrix multiplication, you get a 1, 0, 0, 0, right? And then that gives you that matrix. But if you compute this expression, then you get something that's not comparable in the order. So far, so good. So this notion first of all, this notion does not occur for commutative C-star algebras. If you take any Schwarz positive map, it's automatically going to be, if you take any positive map, it's automatically going to be Schwarz positive. So it also turns out that this forms a subcategory. Schwarz positive maps are closed under composition. So we get yet another subcategory of the original one we had. And this category contains the previous one. Sorry, the positive maps, I always get confused with which one's which. The Schwarz positive is stronger, so positive contains it. So now there's the last notion of positivity that we'll introduce. And this is a notion that says a map is positive completely positive if whenever you take the tensor product of that map with the identity map for any size matrix algebra that you want, then that map is also going to be positive. So physically, what this is saying is that if you have a map, if I think of these systems as quantum systems, and I think of this map as evolving a density matrix or a quantum state, and then I have another system that's right next to it, like this is going to be the n by n matrices. And when I evolve that system in time and I leave that system alone, the one that I'm just keeping on the side, then the resulting map should also be positive. It turns out this is a non-trivial restriction. And it's true that every n positive map is n minus 1 positive, but the converse is not true in general. And it also turns out that every 2 positive map is Schwarz positive, but even the converse of that is not true either. And Choi came up with an example in 1980 with such a map. And this map actually has a very interesting geometric structure. So if you notice, it breaks up into 2 parts. So on the one hand, you take the transpose of a matrix, and on the other hand, you take its trace and you multiply by the identity. Now, we know from the previous few slides that the transpose map is positive, but it's not Schwarz positive. And the right map, trace, turns out that the trace is actually completely positive. So, and what you're doing is you're taking a convex combination of these 2 maps. And at the extreme point of this convex combination, you have something that's positive. And on the other side, you have something that's completely positive. And this is sort of like interpolating between those two maps. And somewhere in between, you hit a point at which you have a map that is actually Schwarz positive, but not too positive. And in fact, the geometry of such things of like when you jump between these different notions of positivity was studied by Choi and Tomiyama in the early 1980s. It's a very interesting work. But anyway, I'll move on and just mention that the category of the collection of CPU maps, completely positive unital maps, also forms a subcategory. And don't worry, in the next slide, I'll show you all of these inclusions again. So I hope that you'll be able to keep track of everything, because this might be quite a bit. But there's the last notion that I want to introduce of a type of morphism in these categories, and that's of a star homomorphism. And these will correspond to our deterministic maps. And these are maps that completely preserve both the algebraic structure and the involution. And you can depict this diagrammatically. On the left, you have the usual notion of determinism. And on the right, you have this property that just says that that map is natural with respect to the involution. So that's an additional axiom that we have. And it turns out that all star homomorphisms are completely positive, but there are completely positive maps that are not star homomorphisms. So it really is that the star homomorphism property is like as strong as you can get besides being an isomorphism. So you also get another subset. Sorry?
Is there compatibility with the star? Is that a completely independent relation of the compatibility, the multiplication?
As far as I'm aware, yes. Yeah. And so we have a notion of a hierarchy of notions of positivity. And so now here's this little mini diagram that I was hoping to show you. So we have deterministic on the far left, completely positive, Schwarz positive, and actually there's a lot more stuff in between all of that too, but I'm not going to focus on that part today. And then on the far right, we'll have positive unital. And actually on the far right, which I haven't even drawn, is the original quantum Markov category that all of these are subcategories of. And by the way, the three on the right here, so these three categories, if you restrict the objects to be commutative C-star algebras, all of these categories are the same. Okay, so now I want to finally bring this example back to the context of categorical probability theory. And in his first draft, Tobias defined what a positive Markov category is. And the definition looks something like this. And you don't have to read it. Just know that there was an initial idea for what the notion of a positive category should be. And this is what that notion looked like. And when I began this work on sort of like a more precise relationship between disintegrations and Bayesian inversion that I was hoping that would hold both in the classical and quantum context, when I saw Tobias's paper, I immediately tried to check if completely positive maps formed a subcategory. I want to know if this notion of positivity also holds in the quantum context. And I couldn't prove it, unfortunately. It might still be true, but I just had a lot of difficulty working with it. But just 2 months later, Tobias updated his definition, and it looked something like this. So if you have a quantum Markov category, and you take a specific subcategory, I'm going to call it S positive inside of that Markov category if whenever you have a composable pair of morphisms that when you take the composite, it is deterministic, then the specific diagram equality holds. And I'll explain what this, we'll write what this looks like specifically in our context in a moment. So first I want to address, why did I call this S positivity instead of Tobias's notion of just positivity? And the reason is for the following few facts. So first, the category of Schwarz positive unital maps is an S positive subcategory of the one we started with. However, if I just take positive unital maps instead of Schwarz positive unital ones, it turns out that they do not satisfy those axioms. And in fact, we can just take our transpose map that we had introduced earlier and check this. So here I've drawn the diagram for, by the way, if you take the transpose and apply it twice, you get back the identity, which is deterministic. So at the very least, we should check this axiom if this equality holds. But if you compute the transpose of matrices and follow the diagrams, you'll see that on the left-hand side, we get B transpose times A. On the right-hand side, we get AB transpose. So it actually doesn't satisfy those axioms. And I think the proof that the Schwarz positive unital maps form a S-positive category is actually not that difficult, provided that you take the following theorem for granted, which itself is also not too difficult to prove either in full generality. But I won't describe that proof, and instead I'll describe the proof of the first claim instead. And this is an interesting fact about Schwarz positive unital maps. The claim is that if you ever have an element on which that map acts as a homomorphism for, then for any other element, if you multiply it on the left or the right, it's sort of like a module map with respect to that given element for all other elements in your algebra. So this is called like the multiplicative property of Schwarz positive unital maps. And we're supposed to use this fact to prove that the following equality holds. So if you follow, right, if you take a C and a B, follow it through this diagram, apply G, multiply with B, and then apply F, and that should be the same thing as the right-hand side. So take such a pair of composable maps and assume that the composite is a star homomorphism. So if we just fix an element C, then, and using the S positivity of G, well then this just tells us, remember that S positivity says if you take the square of an element and then apply G, that's always going to be greater than taking the square of applying each of the parts. So that's the first inequality. The second inequality is, well, now we already have FG on the left. And by assumption, FG is a star homomorphism, so it preserves the product. So that's why that next equality holds. And then if you notice now, there's only one other thing we can use, right? F is Schwarz positive, G is Schwarz positive, and FG is deterministic. So it's the last one. F is Schwarz positive. And that allows us to pull through that last inequality. And if you look at this inequality from the start to the end, we end up with the same thing back, right? The two ends of this inequality are both the same. And then therefore everything else in between is an equality. All of these inequalities are equalities. And in particular, if you take the last two here, then we notice that this tells us that F is multiplicative on the element GC. And by the previous lemma, that means, well, if we take any other element like B, then it acts as a module for that map. But this is exactly the same equation that we had just a moment ago, except for the star. But we're assuming that these maps, it turns out that all positive maps preserve the star as well. And so you can remove that star and you get the same condition that we had been seeking. So because all of those other, because all the stronger notions of positivity imply S positivity, those are also Schwarz positive subcategories. And there's a natural question that you can ask, and it's, is the category of Schwarz positive maps the largest S positive subcategory of the original one we had introduced? That's one question. And another question you can ask is that, are there diagrammatic axioms that characterize the subcategory of positive unital maps? My initial hope was that maybe this axiom would work, but it seems to be not. It seems to be too strong for positive unital maps. So you can ask, okay, well, what does classify positive unital maps? And you can also ask, well, going back to that first definition that Tobias introduced, which subcategories satisfy that axiom? It's also an interesting question. I don't know the answers to these questions. And you can also ask about the monoidal structures too. Completely positive maps are S positive, and they actually also form a monoidal category, but Schwarz positive unital maps don't. So in fact, we have that completely positive unital maps is not only S positive, but it's also monoidal. And so that also leads naturally to the question, is the category of completely positive unital maps the largest S positive monoidal subcategory of the category of C-star algebras? And these are interesting questions because this is another way to think about, so the category of completely positive unital maps physically corresponds to non-deterministic dynamics in quantum physics. So you can ask if these string-diagrammatic axioms actually characterize that subcategory. So I think it's an interesting question from both the mathematical and physical perspective. So these are a lot of maybe technical things, but I think it's interesting from the categorical probability perspective. But let me also illustrate an acute application of S-positive subcategories. So this is, I'm going to call this the no broadcasting theorem for S-positive subcategories. So if you have an S-positive subcategory, suppose it also contains the morphisms for grounding and the tensor product of grounding with the identity. So this is, those two maps here just tell you that I'm going to forget one part of my system, and I want to make sure that my category has that capability. So imagine you have those maps, and imagine you also have a map that duplicates things or copies things, and that there's a way that what you can, and the assumption you can make is that if that duplication map indeed acts as a duplication, in the sense that if you forget one part, then you actually recover the thing you started with. Those are what these two equalities mean. So suppose you have a category that contains these morphisms, very natural from the physical perspective. And then it turns out that this multiplication is commutative and in fact equals the duplication for all the objects. And the proof is also purely diagrammatic. So what I've drawn here are two maps, the blue map and the red map, and these are like the F and G's that we had introduced for the notion of positivity. And if you compose the two, then you get something deterministic because you get the identity back. So you can try to see if your this new multiplication map, this imposter multiplication map, is commutative or not by taking this expression and then using string diagram techniques to rewrite these string diagrams, and then use the use the S positivity to pull things through the diagrams. So the way I went from this equality to the left to the right is by sort of extending from each of these bumps grounding maps. And that's how I got this on the left and on the right. But now that I've written it this way, you can see that F and G are appearing here. And what does S positivity say? It says that you can pull the red block up and you duplicate it. And now what you have is, well, now you can retract the grounding. You can pull the grounding down and then get back just the ordinary copy map that you have in your quantum Markov category already. And then by reversing this procedure, you can go the other way around and show that this map is commutative and equals the copy map that you had before. So actually, I think Tobias actually has this calculation in his work as well. I think I've just reinterpreted it in a quantum mechanical setting. And for arbitrary S-positive subcategories of an arbitrary quantum Markov category. So, good. So I have enough time to talk about Bayes' theorem and disintegrations. Any questions so far, by the way?
See, there was some confusion at one point. Joshua had a question. Josh?
Oh, me and David were just talking in the chat about why is it called copy if it's from A to A tensor A rather than from A tensor A to A?
Right. Yeah, so I think maybe copy is not the best name, but if these are really finite dimensional C-star algebras, then you can take what's called the dual of the map, and that will reverse the directionality of these arrows. And when you do that, you interpret the algebras as actual spaces of states. And the interpretation is that you take a physical quantum state and then you would physically duplicate that state. That would be reading the diagrams from down up. But I'm actually working with the algebras of observables and their complex combinations. So that's like the dual picture. And that's why it's multiplication. So it's really like the dual of copy, but I'm abusing the terminology a little bit. Thanks.
That's it. I think that was the only question on the chat.
Okay. So, so moving on a little bit differently, one of the important notions in probability theory, statistics, measure theory is the notion of measure zero. And as far as I'm aware, almost all uniqueness theorems in measure theory and in probability theory almost always have almost everywhere equivalence built in. You generally never get a unique map, but you often get a unique map up to a set of measure zero. So the same thing happens for C-star algebras too. And there are many equivalent ways to think about what almost everywhere equivalence means. On the one hand, you can take two maps and a positive unidal map on the codomain of those two maps. And I think of such a positive unidal map as representing a probability distribution. And the reason I think of that is because when A is a commutative C-star algebra, it does correspond to a probability distribution. And in the quantum mechanical context, if A is a matrix algebra, then such a positive unidal map corresponds to a density matrix. So these are analogs of probability distributions. And again, because the arrows are reversed, if you think of F as in the dual picture, F is a map going from your, like let's say measure space A to another measure space B, then the measure that you're working with is on the domain. But again, the maps are backwards. So, so on the one hand, you can take the difference of those two maps applied to any element, and then you can ask that the expectation of its square is zero. So I'm calling omega A star A the expectation of A star A, because again, if these are commutative algebras, then this really is the expectation with respect to that probability. So if you happen to take the difference of these two maps and you always land in this null space, then that's equivalent to the following string diagram equation. That's not obvious actually, but it follows from the multiplication theorem I mentioned earlier. And in fact, this is true not only for finite dimensional C-star algebras, but it's true for arbitrary C-star algebras, this theorem. And when this happens, we say that F is almost everywhere equivalent to G with respect to that state. And the first definition appears in joint work with Ben Russo, and the second definition appears in Cho Jacobs. And I was determined to make sure that the two were the same, and they are in fact equivalent in this context. So now that we have this notion of almost everywhere equivalence, you can make sense of it as well for sets and stochastic maps. And for Bayes' theorem, the data that we assume are you have a probability measure on X. You can think of that as your prior, for example. A stochastic map F from X to Y. That's your, sorry, I forget these words all the time, but your marginal likelihood, I guess. Then there exists a map going in the reverse direction that satisfies the following equality. And it turns out that when such a map exists, it is also almost everywhere unique. And the interpretation of this map is that it actually reproduces the usual Bayes law. So the probability of X given Y times the probability of Y equals the probability of Y given X times the probability of X. And I have a video of why I call this Bayes theorem and a more explaining more about what I just said, if you would like to check that out as well. And as far as I'm aware, I think the first person to write down this first part of the diagram was Brendan Fong in his thesis, in his master's thesis. And Cho Jacobs wrote the string-diagrammatic formulation of almost everywhere equivalence. So that allows us to think of Bayes' theorem in this string-diagrammatic way. So that theorem sort of classifies one way of understanding what Bayes' theorem is telling us in terms of going between conditionals. And it motivates the following definition in the quantum setting. If you have a completely positive map and a state, well, then you can, instead of pushing forward a measure, you would pull back a state to get the, so you can pull back the state. And a Bayesian inverse of such a map is a map in the reverse direction satisfying this equality. You can make that into a definition. And then you can ask, well, in this setting, does such a thing always exist? And is it almost everywhere unique? And the existence turns out to not always be guaranteed for completely positive maps, even between finite dimensional C-star algebras. However, they are almost everywhere unique when they exist. That statement is true. And for a linear algebraic theorem characterizing its existence, you can check our work with Russo on specific conditions on when these things actually exist. And it's a very interesting linear algebraic problem, but I won't discuss it here with you today.
Could I ask a question?
Absolutely.
So back in the classical case, could you just go over, you know, what you do in the situation? Like if I'm talking about the conditional of, you know, X given Y, it's typically not defined for the case in the values of Y with the probability of Y is 0.
Correct.
Can you explain how that support issue is handled in this approach?
Yeah, exactly. So the amazing thing about this, the way that this statement is formulated, it's only a statement about the existence of such a map, and you actually don't care about what's happening on measure 0 sets. What you really care about is how unique is this thing. And this thing is always unique up to sets of measure 0. And in the classical setting, like in this specific instance, you don't really care about what you assign to those things that have measure 0 because of the fact that you're working with these probability distributions. For example, if you're doing updating and you think of X as your prior, and then you can push forward that measure to Y. You can now, if you see something new that happens, in general, you have to make sure that the thing that you see that's new, this new incoming evidence, it has to be absolutely continuous with respect to that push forward measure. So your prior has to be, you know, robust enough to allow you to do something like that. And once you make some assumptions like that, then there generally is no issue with the measure 0 setting in the classical setting. Yeah, I don't know if that.
Yeah, that helps. Thank you. And then, so the non-uniqueness in the quantum setting is something that isn't covered by these sorts of continuity arguments.
So you make sense of everything in terms of supports, and you still have a statement that based on the previous definition of almost everywhere equivalence, you still get a Bayesian inverse that is almost everywhere unique. And so if you do, yep. I don't know.
May I ask a comment?
Sure.
Yeah, go ahead.
Yes, so that's the Bayes theorem that you state for the finite set, but in my talk, we state for general, how to say, measurable space. And in more or less the same setting, of course, I do not use the diagram, but probabilistic morphism. But there is something more, how to say, in Bayesian statistics, there are some more certain conditions that you need that's after many updating. Yes, so that's analytically that is a more certain problem, and then you need to discuss more. Yeah.
Absolutely. Even in the continuous setting, it's a very subtle issue. In general, you would only expect Bayesian inverses to be measurable. And even then, you have to make some assumptions on the measurable spaces that you're working with. Although those conditions are not as severe as requiring like continuous inversion. Any other questions?
Yes, sorry, I have a question. So can you explain again just how are you reading these diagrams in the theorem?
Oh, sorry. Yes, I did.
Yeah. Because I'm confused with the P and Q here. Like, it's like, I don't know.
So I should have mentioned, I did switch terminology here, and I think this is the only slide where I actually talk about the dual picture in terms of sets and stochastic maps between them. But you're reading these now from bottom up. And the bottom of this diagram where the triangle points down, you should think of that object as being a single element set. And then that single element set maps to Y, and that's a stochastic map, so it gives you a probability measure on Y. That's what this part of the diagram is.
Okay.
And then the duplication map just allows you to copy the output variable into two separate parts. So on the left-hand side, you really will get, in this case, it would be like Q of Y times it's hard to say this probabilistically, like usually you write P of X times P of X given Y and things like that, but I'm using different letters for all of those different symbols because to me they mean different things. I'm using G, F, P, and Q. Does that help a little bit? Okay.
Sorry. No, I was just saying that, like, yeah, normally people only use one letter P because there is a common probability.
Correct. Correct.
Here you're not supposing a common.
Yeah, I'm trying to avoid that just because.
Yeah, so it's very coherent. Yeah. Sorry, I mean, I was just trying to read the diagrams from top to bottom. So
right.
I think that it was confusing for me.
Yeah, if you're familiar with Bayes' theorem, all of these are the same letter, which I can't.
Yeah, sure. No, okay, thank you.
Okay, great. So I should probably wrap up, but that's okay because I'm basically done. Let me just list some interesting features of this definition. And if you have the same setup that we have before, then Bayesian, well, actually, I can summarize all of these facts by just saying that Bayesian inversion is monoidal, it's compositional, and it's almost everywhere unique when it exists. And it satisfies a lot of things that you would expect, like the Bayesian inverse of the identity or an isomorphism is the inverse, for example. So it satisfies a lot of those very familiar conditions that you would like. Well, with the exception of the fact that they don't always exist. That's probably maybe one downside. And disintegrations are very, very closely related notion. And there exists a definition for them. But roughly the idea is that in probability theory, these turn out to just be special kinds of Bayesian inverses. And when you make those definitions precise, it turns out that disintegrations are also special kinds of Bayesian inverses in the quantum setting. And in fact, disintegrations are closely related to just making the assumption that the stochastic map that you had initially is actually deterministic or almost everywhere deterministic. And the same thing happens in the non-commutative setting as well. So there are theorems in that direction that tell you those things. Although, of course, the definition of a disintegration looks quite different than the definition of a Bayesian inverse. So that's all I really had to say. And a lot of this information can be found in these papers, plus many more in the references that are in these papers. And thank you very much for your attention.
Well, thank you, Arthur, for a wonderful talk. It's you had a good number of discussions. Well, we should thank the speaker again by clapping. I've forgotten how to do that, but we can clap standard. If there are any more questions, we have roughly 10 minutes before the next talk gets started. So if there are any more questions, we can take them now.
Yes, I have more questions.
Mm-hmm.
Go for it.
So maybe maybe concerning your last slide, in fact, because okay, so here you introduce a notion of disintegration,
Mm-hmm.
for which only deterministic maps are disintegrable. But how does this link to the, I mean, there is this discussion in the quantum probability community if conditional quantum probabilities make sense. So do you interpret this result as it is not possible to define consistently conditional quantum probabilities, or this is not the correct notion of a conditional quantum probability?
Yeah, that's an excellent question, and in some sense, like both of those things are possibilities. I think my personal interpretation is that so the motivation for thinking about a completely positive map as an analog of a conditional probability is completely based on the categorical premise that commutative C-star algebras and positive maps between them is equivalent to the category of sets, finite sets, and stochastic maps between them. And then you can either look at positive maps. So therefore, like if you look at the non-commutative setting, you could look at positive maps, completely positive maps, whatever. If you think of those things as analogs of conditional probability, then yes, then this puts a restriction on what things you can do in quantum mechanics. But that's, again, only if you're thinking of, I'm trying to understand what conditional probability is in quantum mechanics from this categorical perspective. There may be ways around it that avoid this perspective and
but when I see your equations here, I think that some people have proposed in the quantum literature quantum disintegrations that do not look like that. Because, for example, if you interpret this as like, for example, with density matrices, so these states are like kind of trace of the density matrix times the state, no? But sometimes people have done like weirder things, like split the density matrix into two square roots and put it one on each side. I think realizing that this is difficult, or maybe it does not make sense always, this is what I have seen, that like people have tried to introduce weirder operations.
Okay, yeah, so that's
well defined, but yeah, maybe they are not justified categorically. I don't know. I mean, it's just that in the quantum realm you have much more flexibility.
Right. So actually, I think this is the important slide that is relevant to your question. So the notion of conditional map that you're referring to, I think, is called the PETS recovery map, also discovered by Barnum and Nill and Leifer. And we actually also have a theorem that says when a Bayesian inverse exists on a very special subspace of your algebra, which is like the corner. So because a projection map splits up a matrix into 4 parts. And if you look at one of those parts, the part where you have the support on both sides, then it agrees with that map. You can actually prove that if the Bayesian inverse exists, it actually equals this PETS map. But our Bayes condition gives us information outside of that corner of that matrix. So, and then it allows us to sort of like extend uniquely in some way because of that additional information. So it's not completely unrelated to that map actually that you're referring to. So in some sense, like this formalism kind of captures some aspects of that map as well. But that map that you're referring to.
But I'm really asking you. I mean, I think this is a very intriguing question. Somehow. Well, I don't want to extend myself, but there are many things that people try to do in the quantum setting that like you are immediately. I mean, these conditional probabilities are really the main difficulty to reproduce a lot of arguments from classical probability in the quantum setting.
Correct. So I'm not.
It's really the thing that does not work well, and maybe this is an essential feature of quantum mechanics. And maybe that we don't want these things to work well, but for me, it's still not clear. And I think there are like even like doctoral theses that say that like quantum conditional probabilities don't make sense, but then other people that keep proposing new definitions. So I don't know.
I think the important thing to note is that, right, in general, when you try to generalize things to the non-commutative setting, there may be more than one option that you can take. And I think each option serves its own purpose. And this is just one of those options. And it serves some purposes. I don't know what all of the purposes it can serve. But it's not equivalent to the other notions that I'm aware of. That's for sure.
Well, thank you.
Thank you.
Any other questions? We still have a couple of.
I have a question.
Yeah.
So it's actually about a similar topic. So at first, I just wanted to ask, do you have a diagrammatic presentation of the definition of quantum Bayesian inverse, akin to the classical one that you presented?
I would call this that.
Okay, yeah, that one. Yeah, exactly. So you mentioned that it could reproduce this proposal with the I like to call it the distortion maps, the one that Leifer and I used and others have used that goes back to the Petz recovery map. So one of the problems with that one is it's not linear in the state. And so is there, like you said, that there might be many proposals that are consistent with this definition. Is there any way to make this linear, or is this?
I mean, even if you do it in the classical setting, it's not linear. Unless if I misunderstood which thing you're taking with respect to, right? Because Bayesian inversion, you actually divide by, if you wanted to write a formula, you
No, what I meant is like, so yeah, like if I have, X and Y, and so I have some prior on X, and I want to compute my posterior in X. So I want to compute P of X given Y. I have P of Y given X and P of X. So if I have a mixture of priors on X, well, the formula for the posterior on X is still linear in that prior on X. Whereas if you're replacing P of X with some density operator, but it appears as a square root of rho, acting on either side, then if I take a mixture of those density operators, convex linear combination of them, the Bayesian inverted state, is not just that. And so that actually is one of the big problems with that definition, is that there's circumstances in which you'd expect the definition to be convex linear. And so the fact that this particular choice doesn't satisfy that is a real problem. Mm-hmm. So that's, to my mind, sort of a big motivation for saying that old definition can only have limited applicability. It can't be a generic definition of Bayesian inverse. But because this is a categorical presentation, I'm having trouble translating it back into the language of CP maps, and I'm wondering, is it clear that this either shares or does not share that problem? Like, is it clear that any definition based on this approach, if I turn it into the language of CP maps, it will fail to be linear in the original quantum state?
I see. So, well, first off, I don't know the answer to your question. It's a good question, and I should definitely think about that, actually. But one of my initial reactions to this is the possibility that because these things don't always exist, my initial instinct is telling me if I take a convex combination, even if it exists for both of them, it's not immediately obvious to me that it'll exist for the convex combination, but I haven't thought about it. So it's definitely a good question to ask, and unfortunately, I don't have an answer. But, yeah,
okay,
thank you.
Thanks.
Well, we should thank our speaker. Thank Arthur once again. And okay. And we're ready to move on to the next talk.